Well, g'day flatties and globe defenders. This is Critical Think from Down Under. Today we're going to talk about the angles to Polaris, and in particular how that doesn't actually work on a flat Earth. Now, this is how it should work if the Earth were flat. Now, flat earthers think that the angles to Polaris do work. This is because they have to manipulate the laws of the universe to make them fit their narrative. So today I'm going to show that everyday observations work quite well with the laws of perspective that we know and love, and not the laws of Flerspective. And if you don't break the laws of physics, then Polaris doesn't work on a flat Earth. We are told by flat earthers that this kind of diagram doesn't take into account perspective. Well, they're actually wrong, and I'll show that. And also, flat earthers will say, due to perspective, as you move away from Polaris, it will appear lower in the sky. And indeed, this kind of thing is true. But they never actually say by how much, never make any measurements to say how much does Polaris move down in the sky. Well, we're going to examine that today. So here are 4 graphs. Each one of them conforms to the rule that as things move further away, they become smaller in angular size. So that's a graph of angular altitude versus distance. Now each one of these graphs has a decrease as the distance increases. However, only one of these graphs can match the physical reality. The others are just lines on paper that have no correspondence at all to what we observe in reality. And you can guess right now that the flat earthers are going to pick the wrong one, because they can't stand it that reality doesn't conform to their desires. Their desire to have a flat earth is completely confounded by everyday observations. So only one of these graphs matches reality. Well, which one is it? Let's listen to Mitchell from Australia as he talks bollocks about angles to Polaris.
So, the first angle I'm going to put at 1 centimetre, 80 degrees with a protractor. Yep, 80 degrees to that horizontal. Horizontal being the GP to the star.
No, the vertical line is the GP to the star.
2 centimetres away, 70 degrees with a protractor. 3 centimetres away, 60 degrees with a protractor to the GP of the star.
To the line.
4 centimetres away, 50 degrees, there's a protractor to the GP of the star. 5 centimetres, 40 degrees to the GP to the star. Yep. That red line, the vertical red line, that is the GP to a star. You can see that they are all equal lengths, and the angle to the GP is shown there. Is this how we see ourselves using a sextant? If we're at that 40-degree mark, are we seeing the side of our heads? Do we see the GP point of that star? Do we see the 90 degrees? No.
Why would we need to see the 90 degrees? We're just sighting the star with a sextant, and we're not sighting some imaginary line that is from the GP to the star. Now the P in GP stands for point. So GP is a point. Again, an example of one-dimensional thinking. And I doubt those lines are all equal length, but never mind.
This is just a representation of what we need. There's no perspective here.
Now this representation is a representation of nothing. This is just a representation of Mitchell drawing some lines with these angles, and they don't represent anything in reality. None of the lines line up to the star, And, well, of course, there's no perspective in that diagram because the whole diagram is bollocks anyway. But there certainly is perspective in orthographic views, and we'll look at that later. Let's carry on.
Once again, the globers love to leave out perspective. Now, this diagram here has a little bit of perspective in it.
Oh, it has a little bit of perspective in it. Is that like being a little bit pregnant? I wonder what it looks like when it has a lot of perspective in it.
It's obviously not at that point where the vertex of the 40 degrees, where the red line meets the light blue line. That's where you have to be with the sextant, measuring an angle to the star. There's a little bit of perspective you can see because the star will definitely drop.
Well, the star's not going to definitely drop. It will appear to be at a lower angle, but the star stays right where it is.
They're all the angles that we measure, the vertexes. The only way that we measure an angle is with a flat, straight baseline. Only.
No. Thousands upon thousands of surveyors will disagree with you. You can measure an angle from anywhere.
Works on a flat earth. It can't take into account perspective. Why is it that you guys don't like perspective? What is it? Why do we have to go side on view?
And no, we don't leave out perspective. It's just that you don't understand exactly what perspective is. And perspective doesn't conform to the way that you want it to work. So you say, oh, we leave out perspective. But the real truth of the matter is we don't agree with your silly Flerspective, and I'll show you why in a little while. Here's another popular diagram that Brandon has bandied about. It's supposed to be showing something about accuracy of linear measurement to Polaris based on or the Flerspective model of vision. Now, I really don't know what this diagram is trying to show. It has no labelling on the axes. It's just a grid of lines, 12 lines in 11 spaces. I'm not really sure why they used 11 spaces. I suppose it just looked good when they drew all those angles in there, 80, 70, 60, 50. And then they're trying to say, oh, look, that's linear. And I can just draw these lines at 80, 70, 60, 50, 40, 30, 20, 10. And just because I'll have to adjust that to 11 squares instead of any number that makes any sense, it seems to magically line up on the green ones. But the yellow and red ones don't line up. Well, this could be because your linear model is wrong. And anyway, the whole diagram makes no sense. It's not backed up by any measurements or anything. It's just a concept that some flatty made up. They didn't try and verify it with measurements. And you know what's wrong with that?
So these explanations are not scientific. They're not backed by any measurable proof. And that is the problem.
Yeah, that's right. PW's got it right. So I'm here to tell you now that perspective doesn't work in a linear fashion. And it's a curve, but these one-dimensional flatties don't understand curves. They only understand straight lines. So they can never understand that perspective is a non-linear relationship between the angular altitude and the distance. And anyway, if I were to plot my points, they would all be along that curve. Well, let's go and do that, shall we? So at great expense to myself, I've constructed this flat Earth model to scale. Well, actually no. I've just picked a bit of our globe Earth that looks flat to me, and I've measured some distances along there. You can see from point A, I've marked in the distances to the nearest metre all the way up to point K. And then these are my measurements of the distances, and I used a measuring device, and I walked it and measured it. And now at point A is my Polaris. Yes, indeed, that street light up there, hanging up there in the middle of the sky. Now, I'm sure that there's an imaginary red line there with a right angle at the bottom, but we can't see it. All we can see is the light in the sky. And we're going to measure the angle between that light and the base of the pole there. So that will give us the angular size of that height, or the same thing as the altitude to the star. Now, I did measure the shadow on the ground when the sun was at 45 degrees. It was a little bit difficult because the traffic there is quite considerable at times, but it was around 9.5, 10 metres. And I took my photo and made a measurement from the photo as well. And because I was not going to lie on the ground to take this photo, I took it from about 1.5 metres in height, and I worked out that the height of the pole to the light is about 9.5 vertical metres. And I did all the calculations from the picture I took there using the field of view that I worked out from the zoom and the sensor height. So it's 9.5 metres here, and it is around 9.510 as measured, and let's go with 9.5 with this. That's close enough for what we're trying to do. So in this photo here, I'm actually 24 metres away. Now, if you recall, the height of my Polaris here is 9.5 metres from the ground. Now, if I was 9.5 metres away from that Polaris, I would be looking up from the ground at 45 degrees. Now, even all you flatties should know that a triangle with 45 degrees has two equal sides either side of the right angle. Now, if we were on our mythical flat Earth and we were at 45 degrees latitude, 45 north that is, and we sighted Polaris, we would see an angle of 45 degrees. Now, we would be 5,000 kilometres away from the North Pole on our mythical flat Earth, and so therefore that Polaris would be 5,000 kilometres high. So here, this is a scale model of our flat Earth here, and it is a factor of about 500,000 to 1. So when I'm 9 metres or 9.5 or 10 metres away from my Polaris, then I'm at the equivalent of 45 degrees latitude. Now, at 20 metres away, I'm at the equator. Now, when you're at the equator, Polaris is no longer visible. According to Flat Earth, it's disappeared due to perspective. But in the real world, here we are. We're further than the equator away from our Polaris on our mythical flat Earth, our flat Earth model here, physical model of the flat Earth. You can see Polaris is still up there in the sky. You can see it easily. So what's going on there, flatties? I don't think perspective works the way that you want it to. The Polaris is easily visible even when you go beyond the equator. Oh, big problem for you flat earthers. So here, when I go further away, yes, it gets smaller and appears lower. Now, I've kept the focal length the same so we can compare these photos, and I've moved further away. Oh, it gets smaller and it gets lower, just as we would expect due to perspective. Now, this is a flat bit of ground. There is no curve, so perspective is not any imaginary curve here. Perspective is working just like it would on a flat Earth, and there's certainly no R required anywhere here. You're not going to need R for this. Anybody can do this. And have a look at this. When I plot the number of pixels that the pole is high to the light, so the number of pixels between the light and the bottom of the pole in a vertical direction, And then I plotted against what we really expect from perspective on a flat plane. Guess what? The actual measurement agrees with the way that perspective actually works. And the Flerspective line, that black line there, is nowhere near it. I mean, we're already beyond the equator, and according to that, Polaris shouldn't be visible. That black line is the linear Flerspective line, the one that's supposed to be how our vision works. Well, my vision doesn't work like that. And certainly when I took that photo, the camera's vision didn't work like that. And look, some of these points here are even way beyond the ice wall. I can still see Polaris up in the sky. Something terribly wrong with your flat Earth, fellas. So here we go. Here's another photograph. Now you can see these lights, street lights. We've got 1, 2, 3, 4, 5. They're all similar size. And yes, according to perspective, they appear to get lower and lower as they get further away. Yes, we all agree with that. But it's the amount that they get lower which is the problem. Now let's just pretend this could be the sun in the flat Earth sky moving away. As it moves away, it gets lower in the sky. Yes, indeed. But that last light there, that last street light is way beyond the ice wall and it's still up in the sky. So the whole premise that the flat Earth sun can set due to perspective, I mean, that's hopelessly wrong. I mean, all you got to do is go outside and take a picture. You can see that's hopelessly wrong. There's no way that flat Earth sun can set. And this could also be distances of Polaris from you, and it's all in the one photo there. You didn't have to move any steps. So there's Polaris this far away, Polaris that far away, Polaris that far away. Yes, it does get lower in the sky, but it never disappears, even when you go beyond the equator. And so that particular one, I counted the pixels on that one and then plotted it again. And again, same thing. Perspective behaves exactly as we would expect. No funky visual things going on, no optical drop. Oh, no extra perspective you have to add in. What you photograph is actually spot on. As you would expect, that's reality. Reality agrees with the way perspective should work. And the poor old Flerspective linear line there is all hopelessly outclassed by real live measurements. Now I've got another photo here. This time I've got 1, 2, 3, 4, 5, 6 street lights in this one. Same deal, but this time I'm going to illustrate the orthogonal view, or as Mitchell from Australia calls it, Muppet vision. He thinks this doesn't show perspective. He thinks we forget about perspective, we ignore perspective. Oh, but perspective is already here, my friend. Yes, orthographic view has perspective built in already. It's too easy. If you take a look at this diagram, see this observation point here. You've got these points across the sky, street lights or stars or whatever you like to call them. You can see they're all above the flat plane there at an equal distance. Yet when you look from over here and you sight that last star, it will appear lower in the sky than that third star because you're looking lower. And so that's how perspective works. You don't have to draw these stars as going down. This line here automatically makes it appear to go down. This diagram is a representation of reality, and from this diagram we can calculate exactly what the perspective angle is for each of those street lights. And when we do that, and we plot everything, we end up that the photograph agrees with the calculations made from the orthographic view. So the orthographic view and perspective are the same thing. You just got to know how to look at it, how to read it. That's all it is. And look at the flat Earth Flerspective line again. Nowhere near. The orthographic view is pretty much spot on to what we photographed. Oh, how about that, flatties? Oh, a pretty sad day for the flat Earth today. Perspective actually works the way we know it's supposed to. Nothing special happens with how your vision works or anything. Oh my goodness. And that clearly shows that Polaris and sunsets just don't work on a flat Earth. So, in summary, observable reality shows several flat Earth claims are bollocks. So perspective is not linear. Orthographic views do account for perspective. Perspective in reality does not support the FE narrative. It does not support the idea of a sunset or Polaris disappearing when you get to the equator. And the angles to Polaris cannot work on a flat Earth. I went out there on a physical model of the flat Earth and it just doesn't work. And the sun cannot set on the flat Earth, as my physical model showed. And things get smaller is not the same thing as things disappearing. Vision works just as we can predict and expect, using an orthographic view, I should say. An optical drop is made up bollocks, and therefore the Earth cannot be flat. Well, thanks for watching. Please like and subscribe, and I'll see you next time.